Oh. Not today, but if you remind me tomorrow, I hope at the end of the lesson I can talk a little bit about lightning strikes if you want the physics of that, but I don't think I'll have time today. What have we learned so far? This, in theory, should be review. Here we have a -2 microcoulomb charge, and we're going to move 75 centimeters to the right. So our field point is right there. Nick, what is example A? What does part A want me to find? What's the symbol, the abbrev, the letter that we use for electric field? Big E. Don't think F, that's force. I know field starts with an F, electric field. So, Nick, I'm going to go like this. E equals. On my equation sheet, I think I have two ways to find electric field. There's this one. And there's that one. Nick, which one am I going to use in part A, and how do I know? Why? You're right. They gave me a distance, an R. So it's going to be K big Q over R squared. How would I know the other one, Mr. Duke? Oh, if they said a test charge feels a force of blah, 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 what's the electric field? And you would say, oh, it's the force divided by the charge. That tells me the magnitude of the electric field. It's going to be 9. Do I put the negative in for electric field for the charge? Okay. 2 microcoulombs all over. Ooh, Nick, what's R? Careful. .75. And don't forget the squared. Can I do this one in my head? Nope. So let's crunch it. Oh, I wrote a 9 instead of a K. It's 9 times 10 to the 9th K, sorry. 9 times 10 to the 9th, 2 microcoulombs divided by 0.75 squared. Are you with 32,000? Yep. Nick, units? Sorry? Coulombs is charge, can't be coulombs because this is not a charge. How can you, Nick, look up? How can you get newtons per coulomb? See, it's hidden in that one, right? Force over charge, newtons per coulomb. Direction. How do we figure out the direction of electric field? We pretend there is a little positive sitting at that location, and we ask, which way would it want to move if it could? Which way would it want to move? You know, since they used the word east, I'll give it as a compass direction. A positive would want to move that way because unlike charges attract, unlike charges attract, so it's going to get pulled. And you're right, I should have drawn a compass rose as soon as I decided to go with east-west. Okay, cool. Camille F., what's part B you want me to find? I don't write this down, look up. I could totally go like this. K, big Q, little q over R squared. And I would give you full credit if you did, except. What did I find in part A, Camille? Symbol, big E. Is there a version of big E that also has a force in it? Get the F by itself, please. Could you write EQ? I won't take marks off, but look up, everybody look up. I'm trying to make that look like this. This QE is the equivalent of the mg, get the obvious one, shortcut if we knew the gravitational field. And I'm putting the q where the mass is because mathematically we've noticed the q's show up where the m's did in gravity. So I'm trying to make it look the same. And this is actually really nice because what is the charge q that we're putting at this location, Camille, according to part B? In fact, it's 2 times 32,000, which you can probably do in your head. Or can we? 64,000, yes? Units, this is a force, so newtons. Oh, it wants magnitude and direction. The charge, this 2, was it positive or negative? So which way will it feel a force? If you said left, I'd give you credit, but since they said east, I'll use west. One of the nice things, if you happen to know the electric field at a location, you got a nice shortcut for finding the force. In the same way, if you know the gravitational field at a location, you got a nice shortcut for finding gravitational force, mg. C says, find a force on a -4 microcoulomb charge. I can do the same thing, Hannah. I can go Q times electric field. Am I going to put the negative in? No. So it's going to be 4 microcoulombs times 32,000. .128?
Yes.
Newtons direction. And I'll say east. Yep. So that's about what we can do with a single charge. And again, notice if I know the electric field, I've got a bit of a shortcut to find the force. What does electric field tell us? Electric field tells us how many newtons of force each coulomb of charge at that location will feel. For energy, there's something similar, except it doesn't tell us how many newtons each charge feels. It tells us how many joules of energy each coulomb has at that location. And we call that potential. Not potential energy, just potential. It's also called voltage. I prefer the term voltage because it's less easy to mix up voltage and potential energy. There is some potential to mix up potential with potential energy. They're not the same thing. But in the industry, if any of you go into electronics, you will find they talk about a voltage potential or a potential difference or a potential all the time. And so even though I prefer voltage, I will use both terms to match the industry. What is voltage? What is potential? It's how many joules every coulomb of charge would have at that location. And the units of potential, the symbol for potential, capital V, voltage. The units of potential or voltage are joules per coulomb, which is defined as a volt. We must be careful not to confuse potential with potential energy. They're different. They're related, but they're different. So what's the voltage definition? Voltage is defined as the amount of potential energy per charge. I think I used a lowercase q. I sort of gave you that on your formula sheet, although there I probably gave it to you as a change in, as a change in, but it works as a single location as well. Did I use lowercase or uppercase q? Uppercase? Okay. What are the units? Joules per coulomb, and that is a volt. What you're going to start to see me do for the next while is, I'm way zoomed in here to 900%, no wonder. It's easy with lined paper to tell the difference between an uppercase V and a lowercase v. Volts, speed or velocity. When it's not lined paper, it's tough. And so I'm going to steal a trick from my college physics professor. Whenever we did a capital V, we always put the little wings like a serif on there, like from a font, and that was capital V. Lowercase v didn't have that, because we are going to run into an equation where we're using V voltage to find V speed in the same equation, and you don't want to accidentally cancel out the V's because they're different. Example 2 says, fill in the proof to find the potential or voltage due to a point charge, Q. Well, we imagine that we move a test charge, little q, to the field point and then find the ratio of potential energy per charge. Potential energy is K, big Q, little q, over R. So the potential energy per charge would be K, big Q, little q, over R, over little q. Energy per coulomb. The little q's end up canceling, and this gives us our equation for voltage. It's K, big Q, over R. Voltage, scalar or vector? Before you turn the page, Max, you might want to write in the box scalar. And you know what? I did say it was scalar right there. Okay. So again, here's a bit of the problem. As you turn the page, if you look at your formula sheet, look up. Voltage. Look up. Keep looking up for a while. Voltage. Electric field. Okay, it gets even better. Potential. Potential energy. Potential. Potential energy. What's another word for potential? Starts with letter V, but it's called voltage potential or potential. There is great potential to get these mixed up, and in fact, that's probably the most common way kids throw away huge marks on the test. I say, find the potential. They give me the potential energy. Well, that's nice. Not what I asked for, and I can't even give part marks, 0. Or I say, find the electric field, and they say, oh, force. Again, thank you very much, but not what I asked for. Can't give you any marks. Can't give you any part marks. This is why at the beginning of this unit, Max, I said you don't want to try and cram this unit all in at the end. It's a nightmare of trying to keep the equations straight. Let's apply some of this. Example 3 says, ooh, good question. Manav, what is A asking me to find? The voltage. Keep going. So I have 2 ways to find potential. I have that one, or that one. Which one do you think I'm going to use? Why? Okay, and this is the planet that's causing the voltage potential. The voltage is going to be K big Q over R. It's going to be K. Do I put the negative in? How do you know? No absolute values. I'll take your question in a second, Caden. Negative 2 times 10 to the negative 6 all over 0.75. What's the voltage here? Negative 2,700? No, am I wrong? 20. 20. I'm totally off. How did I do that? Okay. Oh, no. It's 3 over 4, Mr. Duke. The negative factor of 2. Shoot. What is it? Sorry? Units? Volts. Which is a joule per coulomb. You had a question.
So on the formula sheet, one has to change and the other doesn't. Can they both be change it? Or
What's changing anything? So here you would have to go R initial and R final, and actually go final minus initial. Here, if you knew the change in energy, then you have the if someone has done the final minus initial for you, then you're getting a change in voltage. Or if you know the change in voltage, someone has done the final minus initial for you, you're getting the change in energy. Oh, Caleb, what's B want me to find? Say that again. Sorry, quiet, folks. Now, don't write this down. Look up. I could go like this. PE equals K, big Q, little q over. And if you did that, I would give you full credit. No problem. But what did we find in part A, Caleb? Is there a version of voltage that has potential energy in it? Yeah? Get the potential energy by itself, please. By the way, this is the equivalent of this. The shorter version of potential energy, not the cosmic one. What's Q? Huge. Positive 2 coulombs. That's a massive charge. Don't touch it. You'll die. What's the voltage? Negative 24,000. And I get, without a calculator, man, of negative 48,000 joules. Now, what does that mean? That means if I wanted to take this 2 coulomb charge from here out to infinity, to get it to 0, I would have to add 48,000 joules of energy. I would have to do 48,000 joules of work. What if I put a 10 coulomb charge right there? It would take 240,000 joules of energy to get it out to infinity. Okay. Voltage tells you the amount of joules per coulomb. What if I had a 0.5 coulomb charge sitting right there? Negative 12. And why negative? Because to get it to 0, I have to add energy. I better start negative to get it out to infinity. What does part C want me to find? Also potential energy. Again, since I know the voltage, I'm going to go QV. Am I going to put the negative in? Yes, I am. Negative 4 microcoulombs. And what was the voltage? Negative 24,000. What do you get? Positive.
Positive
0.96, is that right? Units. What does that mean? First of all, like charges. So if I put a negative charge right there and let it go, it will fall up, but it will move. That must mean it has potential energy. It will move on its own when I let it go. Yes, it does. Not much. It's not going to be taken off like a rocket, but it will move away from the negative charge because like charges repel. So both those answers, both the negative and the positive, they do make sense to me if I think about it. What's voltage? It tells us at that location how many joules per coulomb of energy will there be. And this goes to Caleb, Okay, to Caden's question earlier. If we know the change in voltage, what's change in anything? We call that the potential difference in industry. Difference means subtract. Voltage is potential. So you'll often, if you go into the electronics industry, talk about a potential difference. If we know the change in voltage between 2 points, then we can find the work required to move a charge between these 2 points without having to do a 15-line one. Max, can you put your phone away if you're looking at your phone? Sorry, I apologize. I thought you were looking at a phone. My bad. Example 4. This is a great question. I'm not saying I like it, but this was a classic provincial exam question that would just terrify kids. Terrify them. Especially, what is D asking me to find, Ronan?
Work.
Especially if they went force times distance, because to find the force, since it's a vector, you need all these angles. You'd be adding things tip to tail. They didn't give me any angles. It was a deep, dark hole that you could tumble down, but there's a much better way to do it. Ronan, what's A asking me to find?
Potential.
Where?
Point X.
Is there more than one charge? Let's label them. I'm going to call this Q1. I'm going to call that Q2. What does A want me to find, Ronan?
Potential.
Where?
Point X.
I'm going to call that voltage X, and I'm going to argue that's going to be the voltage from charge 1 at X and the voltage from charge 2 at X. How am I going to find voltage? How do I calculate voltage? So it's going to be K Q1 over R1 plus K Q2 over R2. Should the R's be squared? No, that would be electric field. Well, oh, wait, I noticed something else. Ronan, how big is Q2 compared to Q1?
It's the same.
How big is R2 compared to R1?
It's also the same.
I think an even shorter way is going to be to find 2 times the voltage from charge 1. Just double it. Is that okay? So let's plug in our numbers and do that. The voltage at location X is going to be 2 times K times 2.5 microcoulombs over 0.2. What's the voltage at location X? This should work out nice, I think. 225,000 volts? Is that all right? I need a confirmation. Yes? I see people nodding.
If you put 2 on the top, doesn't that see a couple?
If you're asking can stuff cancel, I guess this 2 would cancel with this sort of, it would leave a tan. Don't worry, if the decimals don't match, just do the math.
No, but what?
Where'd this 2 come from? Recognizing these are going to give us identical answers, right?
But it's the same if you put it on top of it, just multiply by it after.
Multiply by?
Like, when it is on top, it's the same as getting it and then multiplying by 2.
Yeah, that's what we did. We did it, multiplied by 2. You guys suck at fractions, not your fault.
Yeah, we do.
Yeah, it's the curriculum. Adam, what's B want me to find? I'm going to do the same argument as Ronan and I did because I noticed the distances are identical again and it's the same 2 charges. So I'm going to say the voltage potential at Y is going to be 2 times the voltage from charge 1 at Y. So it's going to be 2 K Q1 over RY. 2 K 2.5 times 10 to the negative 6 all over 0.35. You know what? I think you can probably just backspace and change the 0.2 to a 0.35, but also I'm doing this in my head. You're not going to get a clean answer. You're going to get a yucky answer, I think. Is it 120 something thousand? 120? So I'm going to write 128,000, but I'm going to leave this on my calculator. Okay. Hannah, what does C want me to find? The potential difference. The word difference means subtract. What do they want me to subtract? What minus what? So the change in potential is going to be Vx minus Vy. It's going to be 225,000 minus answer button. What do you get? So it's going to be 225,000 minus answer button. Max, what'd you get?
96,429.
Okay. Store that on your calculator. It's volts. Thank you. I was going to look at that, but you caught me before I checked my units. Good catch. What's, yeah.
Adam, 5 minutes ago. So he knows.
Okay. Because Adam, tomorrow, you're going to see a question that wants you to find the final speed when we go through a voltage, and we're going to use conservation of energy, and we're going to have a big V and a little v in the same equation, and it's tough to tell them apart if paper isn't lined. You might accidentally start to cancel things that shouldn't cancel. Whoever what? Made the alphabet? It evolved over time. It's mostly Greek, but we use the Roman alphabet, basically. Max, what does D want me to find? Sorry, no, Adam, not Max. I just picked Max. Adam, what does D want me to find?
Don't worry.
Look up, don't write this down. You could totally go work equals change in potential, don't write this down, plus change in kinetic. And then you would say, I don't think anything is moving. And then you could say, what's change in anything? And so you could go K, Q1, Q2 over R5. Oh, wait a minute. I'd have to find how much energy Q3 had, because we'll call that third mystery charge Q3. Then I would find how much final Q1 and Q2 and Q3 had. It's a better way. What did we just find in part C? I gotta be fussy. We did not find voltage. We found a change in voltage. Hey, there isn't one of your voltage equations that happens to have an energy in it, is there? So here's what we're going to write. Work does still equal the change in potential energy. That hasn't changed. Change colors, Mr. Duke. But if I know the voltage, it's Q, change in voltage. Little q, this is the charge that we're moving. Adam, I've scrolled down. According to part D, how big is the charge that we're moving? 1.25 times 10 to the negative 3. What's the potential difference? The change in voltage. I'm going to write 96,400, but of course, you'll use your answer button. How much work would it take to physically move a charge from location Y to location X? And notice, because this is a scalar, we don't need to do any trig. We don't need to find any angles, no tip to tail. What do you get? 121 joules? Anybody else? Yep. So voltage potential, potential difference, the number of joules per coulomb. Allie, if you know the voltage at a location, big time savings. It tells you a lot of information. Next page. So if the charges start at rest and end at rest, and you're finding work, you can say that work equals the change in potential, no change in kinetic. Example 5 says, prove that if a charge starts and ends at rest, the work is just given by Q, change in voltage. I think we already just derived it from our formula sheet, so I'm going to skip example 5. I'm just going to say, we already did. So here's our summary. You can find potential, voltage, by using the definition. If you're told the amount of potential energy a test charge has at a location, you can say voltage is defined as the amount of energy per coulomb. If you want to do work, final minus initial, put a delta in front of the top two, because they're the ones that are changing. You can also find the voltage if you're told the planetary charge that's sending out the electric field, which is causing the voltage, and how far we are from that planet. That one looks like this. Potential energy can be found by using the potential energy equation. But there's a shortcut. If I know the potential, the voltage at a certain location, I can also find the potential energy by going QV. Again, note potential energy and potential voltage are scalars. They have no direction, much like your no direction. If we have several charges contributing potential energy or voltage, just add them numerically, no tip to tail. What's your homework? Here's what I assigned my block C's. Number 1, 2, 3, 4, 5. Skip 6, 7 is good. Skip 8, skip 9. Skip 10. 12 is good. There is no 11. You can skip 13. You can skip 14. Technically, this also means that you can now do every question on the ultimate review, because I know some of you like to get started. Although I'm going to talk about a few obscure examples tomorrow. I called it lesson 5.5, and we'll also explain how TVs used to work. Do 12. Yeah, there is an 11, but skip it. Okay?
Wait, are we doing 11? Skip 11. Why did I circle 11?
This is my class, YouTube. This is my class.